Hey, so today we're going to start talking about quadratic functions. We will eventually get into solutions and solving quadratic equations and things like that. But for today, we're going to talk about functions. And when we talk about functions, generally the first thing we want to get into is how to graph them. And so we'll do that. And start leaning towards the other things I mentioned before, right? So the purpose of today is to be able to graph a quadratic function. Now remember, quadratic function suggests the same thing that a quadratic expression does, right? A quadratic expression is a degree 2 expression. So degree 2 is the highest degree exponent would be a squared term. So this guy right here makes these functions a quadratic, right? So anything that we talk about today only pertains to quadratic functions. All right, first things first, some vocabulary. A quadratic function looks like this. We just saw from the previous screen. So y equals ax squared plus bx plus c. What you will find is that universally speaking, a is always the coefficient on the x squared term. B is always the letter, the variable we would use for the coefficient of the x to the first term. And C is always the variable we would use for the constant. When we get into solving, we will get into using all of A, B, and C. When we are talking about graphing, we'll use A and B a lot. So just know that those, when we talk about A, it's always the coefficient on x squared. When we say B, B is always the coefficient on x, and C is always the constant out there. Okay? Every family of functions has a parent function, which is the simplest quadratic function out there. For our linear functions, the lines, when we're graphing lines that we've been doing lots and lots and lots of, the parent function is just y equals x, where the slope is 1 and the y-intercept was 0, right? But this is the it's the simplest, most basic linear function there is. Same thing for quadratics. Most basic quadratic function is y equals x squared. So that is your parent function. And we want to become very comfortable and familiar with the parent function because we're going to use the parent function to help us graph any function off of it. A quadratic function does have a standard form, and it's what we've been looking at, y equals ax squared plus bx plus c. We want to make sure that we can write the quadratic function in standard form. I want to make sure that it's in standard form before we try to graph. It just makes it a little bit easier. Okay? Parabola. Parabola is the name that we give a quadratic function graph, right? It's basically a U. So we're getting away from lines and getting into a U shape. So it looks something like this, okay? We'll see here in a second why the graph ends up being U-shaped instead of a line like the linear functions. So now both ends of our graph are going to be pointing in the same direction. So here both ends are going up. We really ought to get in the habit of putting arrows on these ends because those ends do extend up forever. Okay? So to continue on, there is an axis of symmetry. If you go back and look at a U is symmetrical. I can cut that U in half, fold it over on itself, right? And so the line that cuts the U, or the parabola, in half is called an axis of symmetry. It is a line, and so when we want to describe that line, we do have to use a linear function, an equation. We'll talk about that some more in a minute. And then there's a vertex. The vertex is the highest or lowest point of a parabola. So go back to here. There is a lowest point in this one, and it's this point right here. That is your vertex. Okay? And if I wanted to try to cut this U in half, I would want to cut it right down through here. And so this is what's called your axis of symmetry. It is a vertical line, and so I want to describe that vertical line with an equation. Remember from VUX, vertical undefined x equals, that tells us that a vertical line equation is always x equals wherever it hits on the x-axis. Here it's 0, so x equals 0. Okay? So that's an example of an axis of symmetry in a vertex. And the last point in my definition, I'll go back to it in a second, from vertex is the axis of symmetry always goes through the vertex. The vertex is always on the axis of symmetry, right? Think about this as an extension of what we're talking about here. The point, or the vertex is a point, and so when we want to describe the vertex, we always want to give it coordinates. And right now, that point is 0, 0. In order for the vertex to sit on a vertical line, like the axis of symmetry, the x-coordinate must always be the same as whatever we have the x equal to in the equation for the axis of symmetry, right? Hopefully that just makes sense. In order for the vertex to sit on this imaginary dotted line called the axis of symmetry, in order for it to sit on that line, the x-coordinate would have to be the same, right, as what the axis of symmetry equation is equal to. All right? And we'll see that all throughout as we graph. All right? So the definitions again here, make sure you can get all that written into your notes. The axis of symmetry always intersects the parabola of the vertex. That means that the x-coordinate of the vertex will always be the same as what the equation is equal to for the axis of symmetry. All right. Here, there's also what's called a minimum and a maximum value, right? The value of a function is always whatever you get when you plug something in for x, right? So it hopefully would make sense that the minimum or maximum value would just end up being the y-coordinate of the vertex, right? Now, minimum value happens if the parabola opens up. Think about that. If we draw our u up, there is a lowest point. That's what the vertex is, right? And so, so the vertex would be there. Since it's the lowest point, then in terms of the y-axis, it would also be the lowest value that the y-coordinate could be. So the y value would give you your minimum value. Okay? So if it opens up, we're going to talk about the vertex being the lowest point and the function have a minimum value. If it opens down, then the vertex would sit at a highest point, and then the y-coordinate would give us the maximum value. Okay? All right. The parent function. Let's take a look at what the parent function looks like, because every function off of that, we're just going to change the shape a little bit and then move the parent function around. We'll talk about how that works in just a second. Okay? We don't know what the parent function looks like. We don't have any idea. So what we can do is what we can always do when we don't know what a function looks like. We can just pick a bunch of x's, plug into the function, and see what y's we get with them, and create points that we can put on the graph. You did this with your linear functions when you first started learning how to graph those. So you can pick any point you want for x and start plotting out some values once you get the y-coordinate that goes with that x. Now, here I'm going to strategically choose a few. Generally speaking, I try to get an idea of what the graph would look like kind of in the middle of this coordinate plane. So I would pick 0 to plug in for x. 1, because it's super easy. Well, the biggest reason is because it's super easy to plug in, right? If I plug in 0 for x, that's easy. You just square 0, and you get 0. So the y that would go with that x-coordinate would be 0, so you get a point 0, 0. And then I would take a look and see what points I would get on either side of 0, and see if that, and start to try to figure out what our graph looks like based on that, right? So that's why I chose -2 and -1 and 1 and 2. Those are some x's on both sides of the vertex. Or sorry, I don't know it's a vertex yet, but there are x values on both sides of 0. and we can get an idea of what the graph will look like. So let's do that. If we plug in -2 for x, we've got to square -2, right? Since x is the base for the exponent 2, that means whatever I plug in for x has to be the base for that exponent as well. So -2 is the base, -2 squared is 4. As a matter of fact, what you're going to find is no matter what you plug in for x here, all you got to do is square it. And so -1 squared is 1, 1 squared is 1, and 2 squared is 4. So here are a bunch of points that we can plug in, or sorry, that we can plot, because they're going to be on our parabola, on our graph. So -2 comma 4 would sit here. -1 comma 1 would sit here. 0, 0, 1, 1, and 2, 4. And that gives us a pretty good idea of what this graph is going to look like. So we can go ahead and, draw our U. I'm trying to make it look like a U, not so much a V like this one does. Right? So go ahead and make this curved more and just make it a U. And that's your parent function. We want to take all of our other quadratic functions and graph it based off of the parent function. I'll show you how in just a minute. Okay? So take a look. The axis of symmetry, we would cut this parabola in half right through here. Right? And so the equation would be x equals whatever hits on the x-axis, which is 0. The vertex is 0, 0. That's that lowest point. And again, if you see, the x-coordinate and the axis of symmetry still have that connection of using the same value, say using the same number. Okay? All right. Now, any other function off of the parent function, a couple of things might happen. Any parabolas can open up or open down. So if I get to another function that's not the parent function, one way they could be different is that the new function could open down instead of up. If that happens, then we'll want to adjust the parent function before we move it. We'll talk more about that as we get there. All right? All right. Opening up or down. Like we said before, parabolas can open up or down. A quick way to tell if a parabola is going to open up or down is by A. Remember A is that coordinate, is that coefficient in front of the x squared term. Remember the parent, I'm going to always remind you of the parent function. The parent function is y equals x squared. And so the A here, if you don't see a coefficient, you know it's always 1. So the A here is 1. Right? It's positive, so that means that the parent function parabola is going to open up. And we just saw that when we graphed it. Same thing here. If A is positive, then even though this is not the parent function, it's still going to open up, just like the parent function does. And so that's not going to be different. Okay? If A is negative, like it is over here, then the parabola is going to open down. That's going to be different than the parent function, and we have to do some adjustments from there. Okay? But that should be pretty quick. Look at A, and if it's positive, the parabola will open up. If it's negative, the parabola is going to open down. Okay? And our new parabolas, or our different parabolas from the parent function, might also be thinner or wider. Some of them can be really, really wide. Some of them can be really, really thin. And A is what will determine that as well. So remember, the parent function is y equals x squared. A here again is 1. Okay? Now, it's kind of counterintuitive. It's going to be opposite of what you think. But as A gets bigger, and we want to make sure that we're looking at this inequality here, as the absolute value of A gets bigger than 1, grows bigger than 1, right? Absolute value means always the positive version of a number, right? So regardless of sign, if A gets bigger than 1, then the parabola is going to get thinner, right? So where the parabola here might look like this, if A is bigger than 1, it might start to get a lot thinner, look something like that. If A is less than 1, the absolute value of A is less than 1. Or really, we want to take a look at if A is between 0 and 1. Then the parabola gets wider. So how do you get to be between 0 and 1? well, that means fractions or decimals. And so the parabola starts to open up a bit wider. Okay? And it's always in comparison to the parent function. So the shape's going to change. If A is something other than 1, then the shape is going to change. Okay? If it's bigger than 1, the absolute value is bigger than 1, then it's going to get thinner. If the absolute value is less than 1 or between 0 and 1, then the parabola is going to get wider. Okay? And again, that's going to change the shape or the direction of the parent function, and so we'd have to do some adjustments to the parent function from there. All right, here's a couple of examples here. This first parabola, would it be thinner or wider than the parent function? Remember the parent function, y equals x squared, where a is 1. Hopefully for the first one you're thinking thinner, because the absolute value of a is 4. 4 is definitely bigger than 1. Also, don't forget that we can tell that right now this parabola is going to open up because a is positive. Here, is this parabola going to be thinner or wider than the parent function? And hopefully you're looking at this and saying wider, because a is now between 0 and 1, absolute value, so forget about the sign. A half is between 0 and 1, so this is going to be wider than the parent function. This is also going to open down, just as an extra question. So both of these functions are going to have a different shape than the parent function, and we would need to adjust the parent function. Okay? So when we graph any function, like I said, we're going to work off of the parent function. The two ideas that we just talked about are going to could change either shape or direction from the parent function, and we'll have to adjust the parent function from there. Any other quadratic function might also shift. It might sit somewhere else in the coordinate plane besides where the parent function does, right? And that is in terms of the vertex. So if we go back to the graph of the parent function right here, what I mean is, this vertex could shift, or the whole graph could shift. One place or the next could shift over here, right? If it's not the parent function anymore and we're looking at different functions, it can do that. Or it could possibly shift down here. And so what we're talking about is, the easiest way to look at this is shifting the vertex. That vertex keeps moving every time I move it around, right? So we're going to talk about trying to figure out if a particular quadratic function is shifted away from where the parent function was. And the way we tell that is by the vertex. Now, you don't know this yet, but the vertex for this first example here is going to be 0, -4. And we'll talk about how to find that in a second. Remember that the parent function, which is y equals x squared, the vertex was at 0, 0. So since these are different, we are going to shift the parent function around. And how we do that is we use the values of the vertex coordinates to tell us. So in other words, since the y coordinate here is -4, y axis moves up or down. Since the y coordinate is a negative, that means that we're going to take the parent function and shift it down. And we're going to shift it down 4 spots. So not only will we shift the vertex, but we'll shift every point on the parent function down 4 spots. Here, the vertex is 1, 2. Again, don't worry about where that came from. I'll show you in just a second. Okay, but this tells us that since the x-coordinate is a +1, that we're going to shift the vertex right 1 spot, or all the points right 1 spot, and up 2 spots since it's positive. Okay? And so we'll use that shift to move our parabolas around. All right, so I mentioned, how do you find the vertex? And this gets us into how we're going to graph any parabola, right? What we probably ought to have here is a step 0, right? Before we do anything, I would say graph the parent function. Okay? But then we're going to find the vertex of our actual function. And in order to find the vertex, we have a mini formula that you're going to have to remember. X equals opposite b over 2a. Okay? Again, it has this little formula, this little deal has an origin. It has a, it does come from someplace. But for now, for us, let's just worry about that it exists, and this is how we're going to do it. Now, opposite b over 2a, so we're going to take the opposite of whatever b is and divide it by 2 times a. That'll give us two things. That'll give us the x-coordinate of our vertex, and it will give us our equation for the axis of symmetry. Remember, the axis of symmetry is a vertical line. It needs an equation, and this x equals opposite b over 2a will give us that equation. Once you have the x-coordinate for the vertex, then you can plug that into the function and find the y-coordinate, and we'll have some idea of how our parent function shifts. So then we'll graph the vertex. I won't necessarily worry about graphing the axis of symmetry, but we'll graph the vertex, figure out how all the other points from the parent function need to shift those points, and then connect the dots in a parabolic manner, or just draw a U, basically, right? So that's what we're going to do to graph. Let's give it a shot, right? So here's what I would do if I were to graph any of these. First of all, I would want to get all of my parent function information in. We create a table. The table here is given to you, but we want to recreate the table that we used before to graph the parent function. Remember that we just chose some x's, and the x's that we chose were -2, -1, 0, 1, and 2. And when you plug those values into the parent function, the y's that you get with those would be 4, 1, 0, 1, and 4, because all you got to do is square whatever you're plugging in for x. So those are all the points on our parent function. Now, before I put the parent function in the coordinate plane, I want to figure out if the direction or shape of the actual function I want to graph is going to change from the parent function. So here's what I actually want to graph. So the question is the direction of that parabola going to be different than the parent function? Remember, the parent function opens up, and this function, the parabola is going to open up because a is positive. Okay, so it's not going to change from the parent function. I don't need to worry about adjusting the parent function yet. The next question is our parabola going to be thinner or wider than the parent function? And remember, that comes from a as well. Since a is 1, it's the same as the a in the parent function, so it's not going to be any thinner or wider. It's going to be the same width. So the direction and the shape are going to be the same as it is for the parent function. So I'm going to go ahead and graph the parent function the way that it is. And so we just go back to what we did before. And this isn't, since the parent function is not the function that we want to graph, I'm going to put it in here as a dotted U. So just so we know that that's imaginary. It's not the graph that we actually want. Okay? And we'll graph the function that we actually want as a solid U. Okay? Now, we need to figure out how to shift the parent function to get to our function. Right? And the way we do that is we go find the vertex for our function. And remember that we start with that little formula, x equals opposite b over 2 times a. We've already determined that a is 1. We've got to come up here and realize that b is 4. Remember, it's the coefficient on the x term. And while we're at it, c is 5. So the opposite of b, the opposite of 4 is -4. And then 2 times a is 1, so we get -4 over 2, because 2 times 1 is 2. -4 divided by 2 is -2. So the axis of symmetry equation is x equals -2. I could draw an imaginary vertical line through -2 on the x-axis, and that would tell me that the u will be drawn around that axis of symmetry. But I'm not going to do that. The graph is going to be complicated enough with the parent function and the actual function in there. So I'll write down the axis of symmetry as x equals -2. again, since the vertex sits on the axis of symmetry, its x-coordinate is going to be the same. So -2. Now, to find the y-coordinate, we've got to plug that into the function. So we've got to take -2 and square it, and then take 4 times -2, and work that out. -2 squared is 4. 4 times -2 is -8. So you get -4 plus 5, which is 1. So -2 comma 1. That means that our vertex for our function is -2 comma 1, which sits right here. Which means that we've shifted the parent function vertex. The parent function vertex, which is right here. We've shifted it left 2 places and up 1 place. That means we want to shift every other point on the parent function graph. Left 2 places and up 1. So this point's going to end up right here. So this point right here, we'd shift 1, 2 spaces and up 1. So it would be right here. This point, we'd go left 2 spaces and up 1, so end up right here. And this point over here, we go left 2 spaces and up 1, so end up right here. Okay, so we're just shifting everything over. You don't need to draw in those shifts every time. I just did it here to show you. And so we draw our U, and then we're done. Left 2, right 1, you could have picked up just by looking at the vertex as well. Since the x-coordinate is -2, that means we want to take all the points and shift them left 2. Since the y-coordinate is +1, we want to take every point and shift them up 1. Okay? Hopefully that makes enough sense. Next example we'll do together, we'll do a little bit quicker. Okay? And so here it is. Again, get the parent function in here first. Parent function is y equals x squared. So I'm still going to create my table with -2, -1, 0, 1, and 2. And if I were to plug those values into the parent function, I would get 4, 1, 0, 1, and 4. This table is going to be the same every time, at least initially. Okay? All right, before I shift the parent function, I want to find out if my my actual function is going to open up in a different direction or have a different shape. Remember that a for the parent function is 1, so if a for our actual function is anything other than 1, then it's going to either change direction or shape. And if we look over here, this function does have an a that's different than 1. It's -3. So that tells us 2 things. Number 1, our actual function is going to open down now instead of up. And it should be thinner because 3 is bigger than 1. Okay? So since our actual function is going to change direction and shape, then I want to adjust the parent function first before I try to shift it. And I'm going to adjust it before I graph the parent function as well. So what that means is, since a is the value that changes the direction and or the shape, I want to take a and I want to change the parent function. And the way I do that is I just multiply the y-coordinates by whatever a is. Right? So we're going to take the y-coordinates and multiply by -3. So 4 times -3 is -12. 1 times -3 is -3. This is 0, -3, and -12. And so now what I've done is I've created new points. This point, this point. These are all going to be points on your adjusted parent function graph, right? So we go -2, -12, which will sit down here. -1, -3, 0, 0, 1, -3, and 2, -12. And that is your adjusted parent function. That's what our graph would look like before it shifted. So I want to make this a dotted U. It's not really our graph yet because we haven't shifted it yet. But since the shape and the direction are going to change, I wanted to adjust the parent function first and then shift it. So now we're going to try to shift. We've got to go find the vertex. We use our little formula x equals opposite b over 2a. We already know that a is -3. B is 12, C is negative 7. All right, so the opposite of B is going to be negative 12. We go 2 times negative 3. So we get negative 12 over negative 6, which is 2. So the axis of symmetry equation is x equals 2, which means that I could draw an imaginary vertical line through 2 on the x-axis, and that will cut the u in half, the parabola in half of our actual graph. It also tells us that the x-coordinate for the vertex is going to be 2 for our function. And to find the y-coordinate, we just want to plug that in. And so we get y equals negative 3 times 2 squared plus 12 times 2 minus 7. And we work that out. We get negative 3 times 4, which is negative 12. 12 times 2, which is 24. So we get 12 minus 7, which is 5. And so we get 2 comma 5. That's our new vertex. Okay, I need to change colors here. So 2 comma 5 puts us right here. That's our new vertex. And whether you want to look at the coordinates for the vertex and know that we're going to shift right 2, up 5, or if you want to look at how the vertex from the parent function got moved to the new vertex, which is right 2, up 5, either way, that tells us that all the points on this adjusted parent function must go right 2 and up 5. So this point right here is going to go right 2, up 1, 2, 3, 4, 5, and end up there. This point right here is going to go right 1, 2, and up 1, 2, 3, 4, 5, and end up right here. This point right here is going to go right 1, 2, and go up 1, 2, 3, 4, 5, and end up right here. And this guy is going to go right 1, 2, up 1, 2, 3, 4, 5, and end up right here. And then we can draw our parabola. Okay? And now the parent function, or the adjusted parent function, has been shifted. Hopefully that makes sense. Let's try another one. All right. First things first, get our parent function in here. So our table, negative 2, negative 1, 0, 1, 2, 4, 1, 0, 1, and 4. And again, that comes from just plugging those x's into the parent function. All right, so we go here, here, wait. We might need to adjust the shape and the direction first, right? So we look over here in the A, and our actual function is 2. So the direction is not going to change. It's still going to open up, just like our parent function does, but the shape is. It should be thinner again because this A is bigger than 1. So I want to take all the y coordinates for the parent function and multiply them by 2. So we get 8, 1, 0, 8, 2, 0, 2, 8. And that creates new points. So we're going to plot those. Negative 2, comma 8. Negative 1, 2, 0, 0, 1, 2, and 2, 8. Okay, so now that we've adjusted the shape of our parent function, we want to shift our parent function to get our actual graph that we want. And again, that comes from finding the vertex and the axis of symmetry, which is our opposite B over 2A formula. B is negative 8. So opposite of B is going to be positive 8. 2 times 2, which is 4. So 8 over 4, which is 2. So our axis of symmetry equation is x equals 2, and our vertex is at 2 comma something. That something comes from plugging the 2 in. So 2 squared is 4. 4 times 2 is 8. Minus 16 minus 1 gets us negative 9. And so that's our new vertex and how we're going to shift all of our points. We want to go right 2, down 9. So the vertex 4, our new parabola is right 2, down 9 should end up right here. And if we shift every other point right 2, down 9, we should end up sorry, right here, and then right here. Just taking every point and counting right 2 down 9. And then draw your U. It doesn't have to be a perfect U. Okay? All right. Next one. Looks like this. Get our parent function in. Remember, parent function is y equals x squared. -2, -1, 0, 1, and 2, 4, 1, 0, 1, and 4. Next task is our actual function going to change shape or direction from the parent function? And if you look at A is different than 1, so the answer to that question is yes, it's going to change. It's going to open down instead of up. So I want to take and adjust the parent function. Again, we're going to take the y coordinates and multiply by -3. So we get -12, -3, 0, -3, -12. And we want to go plot those points. And then draw your parabola. Okay? Now we want to find out what the shift is. Okay, and that means find the axis of symmetry in the vertex. So opposite B over to A. B here is, well, it's missing. So B is 0. Remember, B is supposed to be the coefficient on the x to the first term. There's not an x to the first term. So B is going to be 0. Here C is 9. Be careful not to let B be 9. It's not. B is 0. Okay? So we go opposite of 0, which is 0. 2 times A, which is -3. And we get 0 over -6, or just 0. So the axis of symmetry is at x equals 0. The vertex, the x coordinate, is 0. So we've got to plug that in and find the y coordinate. That makes this very easy because 0 is always easy to plug in. 0 plus 9 is 9. And so the y coordinate for your vertex is 9. So 0, 9. That means that we're going to take every point on the parent function and just shift it up 9 spots. So here's the vertex. Every other point we're going to go up 9. And get your points right here. And there we go. Okay. Is this making sense? I'll let you try this one. Go ahead and try to graph this guy and this number 5 right here. You can stop the video, give it a shot, start it back up, and see how close you were to remembering how to do it. Okay? All right. First things first, get the parent function in here. X, Y, so we go -2, -1, 0, 1, 2, 4, 1, 0, 1, 4. Look to see if the A in your actual function is different than the A in the parent function. And it is. It's not 1. So we want to adjust the y coordinate of the parent function, multiply it by A, which is -1/2. Right? So 4 times -1/2 is -2. 1 times -1/2 is -1/2. This is 0, -1/2, and -2. So now I want to graph those points. -2, -2. -1, -1/2. So remember that you just go halfway between 0 and -1 on your grid line there. We go 0, 0, and then we're back to the same on the other side. And so that's our adjusted parent function. We want to make this a dotted U again. And this is going to be a little bit wider, right? So our function is going to open, obviously is going to open down, and it's going to be wider than the parent function because a is now a fraction. Okay? The vertex you should have found by doing your opposite b over 2a. B here again was 0. A is negative 1/2, so we get 0 over negative 1, or just 0. So the axis of symmetry is x equals 0. The vertex is 0, comma. Plug in 0 for x. Makes this pretty easy. This is 0 plus 1, or just 1. And so we get 1 here. All right, so that means that our new vertex is at 0, comma 1. It also means that we're going to shift every other point up one spot. So here, up one spot, up one spot, up one spot, up one spot. And there you go. So hopefully you got that. Okay? All right. One more for you here. Stop the video, graph this. When you start it back up, you will see everything, all the work done. I won't walk you through this one. Let's let you check it out and see what you're still forgetting. Hopefully nothing, right? Start it back up. As long as you're good, then start the homework. You can always come in and see me during STAR if you have some more questions. And there you go. There's all the work for graphing that one. Hopefully your graph turned out to be the same. If not, come in during STAR, get some help. We'll figure it out. Go ahead and start the homework and have it done by next time.